Hi, we're going to look at AP Review 2. This one focuses on problems involving areas and volumes. While this has changed a little bit in the last few years, this is a really solid packet. There are 11 questions, and you can see it's pretty much every year we get asked about area and volume. So let's take a look at number 1, part A. Says you've got y equals square root of x, and you've got y equals e to the minus 3x, which we know is exponential decay. Y equals e to the minus 3x, and the vertical line x equals 1. X equals 1. And so this is our region, and we're going to be doing stuff with this region in this problem. Okay, find the area of R. Well, I can simply do a top minus bottom here of square root of x minus e to the minus 3x dx. This says with calculator, which is great, but what about the bounds on our integral? Well, I know I'm stopping at 1, but where am I starting? I need to find that point of intersection. So I'm going to have to graph these functions. Y equals square root of x, and y equals e to the minus 3x. And zoom 6. Ooh, I can barely see that, so I'm going to change this to be negative 1 to 3, and negative 1 to 3. That's better. Second, calculate, intersect. And I get 0.2387. Okay, so we'll just do this problem on the calculator. It'll be the integral. Actually, I think for the purposes of this video, since this is going to happen on the calculator, and you know how to do this on the calculator, I'm not going to waste your time typing it into the calculator. I'm just going to tell you that I got 0.589. That's the area I got for number 1, A. Yeah. And then part B says, find the volume of the solid when R is revolved around the horizontal line y equals 1. Well, y equals 1, since x equals 1, I plug a 1 in there, I get 1. This is y equals 1. And so we're taking this region and we're rotating it about that line. Okay, well, this looks like washers to me. And so for part B, I'm thinking about pi big R squared minus little r squared dx. And I'm integrating from that same 0.2387 to 1, the same bounds that I had for the first problem. My challenge here is going to be to identify big R and little r. Well, little r, and let's change colors, maybe you can see it a little better. This is my little radius here, and my little radius is not 1. It's not this curve, but it's the difference between 1 and this curve. So big R is going to, oh no, that was little r. Little r is going to be 1 minus square root of x. What about big R? Well, big R is down here, all the way to here, and again, this is the y value for this function. This distance is 1, and this big R radius is going to be 1 minus this y value. So big R is going to be 1 minus e to the negative 3x. So this problem becomes pi 2387 to 1. And we've got big R squared, 1 minus e to the minus 3x. Don't forget the squared. Minus 1 minus square root of x squared dx. We really need to pay attention to defining carefully our big R and our little r, because it's big R that's getting squared and little r that's getting squared, and then we're subtracting. Also, don't forget this pi out in front. I wrote my answer in terms of pi and not in terms of pi. Either is fine unless the directions specify one particular way. I had 0.453 pi or 1.424. Okay, and then on part C, it says the region R is the base of a solid. This time, solid perpendicular to x-axis is a rectangle. Okay, so I have this, I have this, I have this, I have this cross section, and I have this rectangle. And so this distance, let's call it d, and the height, they tell me, is 5 times that distance, 5d. So when I go to do the volume here, I'm integrating area, which means I'm integrating 5d times d, or 5d squared dx, and I'm going from that same point 2387 to 1, which is very convenient. Now all I need to do is define the length of d. Well, I can see that d is changing as x goes this way, and it's always based on what's up here and what's down here. So I think d is top minus bottom. So this is going to be 5 integral 0.2387 to 1 of top square root of x minus bottom e to the minus 3x. Don't forget that was squared. This was d squared dx. Remember, finding volume, I'm integrating area. When I computed this on my calculator, I got 1.554 for the volume of the solid. Volume equals. Okay, there's problem number 1. Let's take a look at problem number 2. Problem number 2 says region enclosed by y equals the square root of x minus 1. So that shifts the graph right 1. The x-axis and x equals 10. So we know we have here the ordered pair 10. 10 minus 1 is 9. Square root of 9 is 3. So this is our region. And what are we doing with it? First, we're finding the area of that region. So that's just going to be the integral from 1 to 10. Many students in 2004 put 0 to 10 here. So watch out for little details like that. And all we're doing is finding the area, so we just have to integrate x minus 1 dx. This problem says with calculator, so I'm just setting it up. Really, that's it. I'm not going to try and do it by hand. And then I'm going to pull out my calculator and evaluate, and I should end up with 18. This earns all the points. Don't do anything else. You're wasting time and risking mistakes. Okay, part B says find the volume of the solid R is revolved around y equals 3. So here's our y equals 3, and we're taking this region and we're spinning it around. Now I see that my little radius is going to be 3 minus this y value here. And that y value is square root of x minus 1. My big R is a constant, right? It's always going from here. It's always going from here. And so that big R is 3. And so my setup here would be the integral from 1 to 10. Don't forget the pi out in front. big R squared minus little r squared, 3 minus square root x minus 1 squared dx. We want to see the setup. Don't stint on the setup. Definitely show it, and then you can reach for your calculator and evaluate. I got 67.5 pi, or 212.058 for my volume here. And again, this would be all I would need to show. I don't even need to show both of those, just show one of them. Part C. Part C says find the volume of the solid. This time we're spinning around x equals 10. Okay, so I have this region, and now I've got this vertical line, and I want to rotate this around that vertical line. So most students think about this problem as circular disks, where this is the radius, and we know that this distance is 10. We know that this distance is x. So my equation then becomes, or my little r is 10 minus x. If I'm doing circular disks this way, notice these are dy thickness disks. And so I'm integrating from 0 to 3, not from 1 to 10. And this is a dy integral. And I know I'm doing pi radius squared, but my radius, 10 minus x, isn't in terms of y's. So I need to take this equation over here and solve it so it says x equals. I've got y equals square root of x minus 1, which means y squared equals x minus 1, or y squared plus 1 equals x. So here I'm going to replace this with y squared plus 1 squared. Or I should say, my radius is y squared plus 1. No, my radius is 10 minus x. This is x, and 10 minus x, and I want radius squared. There we go. Okay, so I do this on my calculator. This is 2c, and I get 129.6 pi, or 407.150. I'm probably giving these answers as opposed to the pi answers if I were taking the AP exam. Let's take a look at this problem, though, one more time. This time, let's look at it and see if we would like it better or find it easier to do it as a shells problem. Again, we've got this region that goes from 1 to 10, and we're spinning around this, and so our shell now looks like this. Well, you know, I still need that radius of that shell, and that radius is still 10 minus x. The height is y, or square root of x minus 1. But what I like about doing shells here is that these, I'm now integrating this way, and so I have a dx shell going from 1 to 10. Don't forget that 2 pi constant out in front. My r and my h. And you'll get the same answer by setting this up and using shells as you would disks like we did the first time. I actually think this is a little easier because I don't have to solve this equation for x, but either way is fine, and they don't specify in the problem. Let's take a look at number 3. Problem number 3 from 2005. This problem says you've got f of x equals 1 plus sine 2x, and we've got g of x equals e to the x over 2. This problem is with calculator, so probably the first thing I would do would be to type these into my calculator. If for no other reason, then I'm going to have to find that point of intersection up there. They tell me this is F and this is G. Sometimes they don't tell me stuff like that. I kind of appreciate it. So if I go to graph these, I've got 1 plus sine 2x, and I've got e to the x divided by 2. Remember, because it's a trig function, you want to make sure your mode is set in radians, and then graph. And I can see this region here is the same as this region here. I might as well, since I have this, do second calculate intersect. And I get 1.1356925. This appears to be intersecting at 1. At x equals 0, if I put a 0 in here, I get sine of 0 is 0 plus 1 is 1, and e to the 0 is also 1. So I know this is 0, 1, and over here we have 1.135 6923, comma 1.764468. Okay, so let's see what they want us to do here. They want us to find the area of R. Again, that's just a straight top minus bottom problem. Integral of f. In fact, since they've defined f and g, all you have to do is write f minus g dx here. You do have to claim the boundaries. These are x bounds for my dx integral, so I want to use the x coordinates for the point of intersection, 3, 5, 6, 9, 2, 5. And when I do, I get, for this problem, 0.429. Okay, part B says we'd like to know the volume of the solid when R is revolved around the x-axis. So we're going to take this region and we're going to rotate it around the x-axis. I can see I have a little radius and a big radius. It looks like my little radius is this y value, which goes to this function, which they tell me is g of x. And I'm thinking about pi big R squared minus little r squared. So for us, that's going to be pi. Our little r is g, and again, you can write g of x here squared because they've defined g of x equal to this. You could also, of course, write e to the x over 2 squared. That's fine. And then what else did we need? We needed big R. Big R is this distance. It's the y value to the f function. And so again, we could write f of x squared here, or if we wanted to, we could type in or write in 1 plus sine of 2x and just make sure we square that whole quantity. I kind of like this g and f approach since they went to all the trouble of defining them for me. Don't forget, though, you also need bounds here. We're going from this x value to this x value, so we're going from 0 to 1.1356925. And when I do this integral, I end up with, what did I end up with for part B? I got 1.358 pi, or 4.266. Okay, and finally part C for number 3. It says the region R is the base of a solid. the cross sections perpendicular to the x-axis. Please don't always assume it's going to be the x-axis. Sometimes it's the y-axis, and you lose a bunch of points if you do the x-axis when it says y-axis. Are semicircles with diagonals extending, diameters extending from F to G. So if I think about what's happening here, I've got this situation. We here, and now I've got this, and I've got a semicircle, and I've got this and a semicircle, and this and a semicircle. Okay, so what about, we know we're integrating area, and so we know that's pi r squared, but wait a second, we don't want whole circles, we want half of a circle. And so what we need to do, since this is a dx, these are going to be x slices, we need to determine what the radius would be in terms of x. Well, I see that the diameter is top minus bottom. Now the top curve is RF, and the bottom is RG, and that's diameter. Or that's that whole distance, or the diameter of that semicircle, but I want radius, so I need to divide by 2. So then this is my radius, and remember we wanted pi r squared divided by 2. So my integral, when I pull out those constants and go from 0 to 1.135695 is going to be that radius, which is f minus g over 2 squared dx. And really, you can just leave it like that and type that into your calculator. You've already typed in f and g into your calculator because we needed to find that point of intersection. When I do, I ended up with 0.078, a very tiny volume here. I'll just confirm that in my work. And my work said, pi r squared. I typed it all in. I had the subtraction, and it looks like 0.078. Okay, so there's problem number 3. Let's take a look at problem number 4. Sometimes I feel like these problems, if I've had enough practice with volume problems, that the thing that takes the most amount of time is this idea of typing things into the calculator more than the setup. But maybe you're still working on your setups. More practice, Kukla bellowed. Okay. So number 4 says, and this is also with calculator from 2006, and it says, I don't know, have you noticed a similarity between these problems? Look, there's find the area of the region, let's spin this thing around something, and let's do cross sections. Or let's spin it around 2 different things. That's a pretty reliable set of asks. So what do we have here in problem 4? We've got y equals ln of x. We've got y equals x minus 2. We know what those look like. There's x minus 2. There's ln of x. No. That isn't, is it? That's negative x plus 2. Let's try again. There's ln of x, and there's x minus 2. And here's our region. Okay, so what are we doing first? And of course, we're finding the area of the region, so we're just going to do top minus bottom, which is ln of x minus, don't forget these parentheses, x minus 2 dx. If you leave the parentheses out, you don't get plus 2 like you need. And what is it that we need? Well, we need some boundaries here, and I don't know where these curves intersect. They don't intersect at any place obvious, So let's pull out our calculator and graph. We've got ln of x, and we have x minus 2. And one of the things I appreciate about these problems is that these are fairly straightforward, simple functions, and I can do all kinds of more complicated math with them. Okay, so I don't quite see the bottom. I'd like to change my viewing window a little bit. Let's make the y values go down to -4 and try graphing again. That feels better. Oh, and I need to go a little to the right, I guess. Yes, x minus 2. So, how about 5 there? Okay, so I see what I need to. I do second, calculate, intersect, bring my cursor close to the point of intersection and hit enter 3 times. And I get 3.146192, comma, 1.146192. Some people call this point B, and I want to talk about that in a minute. Let me find this other point of intersection. Second, intersect. Bring our calculator cursor over close to the point of intersection. We don't want it to be confused and find the same point we already found again. Enter, enter, enter. And I get this other point, which I'll call A, to be 0.1585934, 1585934, and -1.841406. Great. Okay, so here's the thing that I don't like about this labeling of A and B, because what I see students do when I grade the AP is that they do this. They write A to B ln of x minus x minus 2 dx. The problem is, when you look at B, there's an x value and a y value. Which one am I using here? And when I look at A, am I supposed to use the x value or the y value? Now, I know, because this says dx, that these should be the x values. But I can't know that the student actually knows that. And as a result, I can't really give anything more than a setup point for this. This student is not going to get most of the points. They may not even be eligible for the answer point in some situations. So please, it may take a while, but it's definitely worth you writing 3.1461932 up here and 0.1585944 down here. You know what I like about doing this is that when you do, you're saying these numbers inside your head so that when you go to evaluate this integral on your calculator, when you go to type those numbers in, they're already starting to be in your head, and so it makes typing them in slightly easier. Okay, so for 4a, I got 1.949 units squared for my area. For b, it says find the volume when the solid is rotated about the line y equals -3. Well, we know that this point of intersection is -1.8. So -3 is down here. Y equals -3. And again, we're going to rotate around this axis. So I'm going to have a little radius, and I'm going to have a big radius. Now, my little radius is this distance. That's little r. Let's be clear, this is -3, and this distance here that you can't really see, this distance is the y value for the curve x minus 2. Well, this distance is -3 minus that y value, right? I'm taking this distance, and I'm taking this away from it to get this distance. So, little r is going to be negative 3 minus x minus 2. If we distribute, we get negative 1 minus x for little r. You don't have to distribute. I'm just doing it there out of habit. What about this big radius? Well, the big radius is the same sort of deal. We know that this distance is y. We know that this distance is negative 3. And so the total radius is this y value here, plus this negative, or y minus, there we go, top minus bottom. Just say top minus bottom, people. Top is y, bottom is negative 3. And so we've got ln of x plus 3. Okay, so then our integral setup. Do I like top minus bottom here? I like top minus bottom here. So top, x minus 2 minus the bottom. The bottom was negative 3. And so we end up with x plus 1. Oh, I like that better than that. I'm not so worried about this because I'll be squaring these radii in a moment. But yes, let's think about that radius as top minus bottom. Top is x minus 2, bottom is negative 3, and so we get x plus 1. So our integral expression here is going to be pi big R squared, which is ln of x plus 3 squared minus, and our little r is x plus 1 squared dx, and we're going from 0.1585934 to 3.146192. When I did this, and I believe this was my setup, I don't think I tried to do this as shells at all. When I did this, and that's exactly what I had as my setup, I had 10.886 pi, or approximately 34.199 units cubed. Okay, there's my volume. And I like just writing the integral, an equal sign, and my answer. It's very clean. It shows the reader I know what I'm doing. I really shouldn't need to do any other work there. What about problem 4? Write but do not evaluate an integral expression that can be used to find the volume of the solid when r is rotated around the y-axis. So I want to take this region and I want to rotate around the y-axis. So I want to rotate around this axis. And when I do that, you know, I could do this and this, but that means rewriting these as x equals functions. And I'm sorry, I still have a number of students who would be uncomfortable, A, conceptualizing that, and B, executing that to be e to the y. So you can do it. Our little r is this x distance, which is the x distance for that curve. And we know that if y equals ln of x, then x equals e to the y. So the little radius is x, which is e to the y. And then the big radius is this distance. It's also an x, but it's the x that goes to the other curve, which is y plus 2. And so we could write the integral, don't forget the pi, and we're integrating x's, so 0.1585944 to 3.1461932 of big R, y plus r. We're integrating this way, Mr. Cooper. Why are you putting x bounds on here? I don't know, because I'm an idiot. So I'm going from negative 1.841406 up to 1.1 4.61932. Okay, so we've got y plus 2 squared minus e to the y squared dy. Now they don't want me to integrate. They just said write the expression. So I'm going to write either that expression or the one that I preferred to write was to think about this situation in terms of Earth, in terms of shells. I know some of you still aren't very comfortable with shells, despite cutting up cake in the form of shells. But I notice here that my radius is x, and my height is top minus bottom. So 2 pi radius x, top minus bottom, ln of x minus 2 dx, and these are x's, so I'm going from 0.1585934 to 3.1461932. All right, I find that much easier on my brain than trying to write this dy integral up here. But you know, you do you. As long as we get the same one of these integrals, I'm a happy camper because I know you're going to be getting those 3 points. Okay, let's take a look at problem number 5. Problem number 5 says let R equal the region bounded in the first quadrant by square root of x, and y equals x over 3. This is with a calculator. It's only at problem number 7 that we run into one that 7, 8, and 9 are with 7, 8, 9, and 10, 11 are without calculator. But most of these are with calculator. We've got our square root of x. We have our x over 3. This one is with calculator, so even though I might think about setting this equal to this and solving to find that point of intersection, I'm just going to use my calculator to find that point of intersection because I got places to go and things to do. So let's change this to square root of x, and let's change this to x over 3 and graph. Boom, 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 boom. Ooh, look, that's way out there. Okay, so